Let's start the question. So example 1, consider that oil flow is steady. If it's steady, then the density is negligible, if you remember. Okay, when flow is incompressible, okay, sorry, when flow is incompressible, rho is constant. Okay, but yeah, so in this case we are incompressible. Steady is just saying that it does not change with time. Okay, do not change with time. A steady flow does not change with time. Okay, by a steady flow we mean that the velocity and the properties at a given location in the flow do not change with time. Okay, this is steady flow. Okay, and then incompressible meaning the density should be destroyed. I mean cancel because it's constant. And then two-dimensional, and then laminar flow, and the vertical velocity component V is negligible. So you're talking about two dimension and then vertical velocity is negligible. So all in all you're talking about only one dimension now. So apply the Navier-Stokes equation for motion with appropriate boundary conditions. So with this thing explained earlier, so we just start off with all of this thing. So derive an expression for the horizontal velocity component U of the oil film. So if you remember back our oil film, okay, so this thick thing over here is the oil film. Okay, this blue color thing. Okay, this thing. This whole ring of blue colors is the oil film. Okay, and then you are tasked to actually derive a horizontal velocity component for it. Okay, so in order to derive this, we have to apply boundary conditions to solve for the constants of integration, because you have to integrate the equation, the Navier-Stokes equation. As you can see, the Navier-Stokes equation is in terms of um, the highest order is actually second order, so you have to integrate twice. Okay, in this case, and then you may say, why don't you integrate this one? Because yeah, actually this whole piece is one equation. Okay, in the end later you'll see that we eventually um, we are eliminating all this except the u. Okay, so I'll just go on first. So we have to first set in our parameters. So this steady, incompressible, whatever, then we just sub it in. So for steady state 2D flow, okay, assuming V is negligible, so one dimension, we only look at the changes in the x direction only. And therefore, this is the equation, okay. So if you remember back, this is our template, right? So this is the u velocity, u velocity, u velocity, u velocity, and then we have a in the y direction, okay, x direction, sorry, and then this is the u and the u and the u. Okay, we have a square, 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 fx. So I'm just filling out the blank. Just let you see that this template is pretty easy to use. And then we assume that steady state. Okay, so steady state wise, um, time doesn't change. Okay, so it's negligible. And then we also assume that it is incompressible. So we can also cancel this one. So this is also incompressible. And thus we are left with and also V is negligible. Okay, and then 3, we are talking about 2D flow, so Z direction is cancelled. Okay, and then V is negligible. So V is negligible means that there will be no Y axis, so you're talking about only one direction. If you remember, this is X direction, Y direction, and Z direction. So we're talking about only X direction over here. When Z goes to minus partial P over partial X. So this is the pressure gradient. The rest of this doesn't change much, I would say. Okay. Yeah. Hold on. Let me repeat the whole thing again. Okay. For steady state, okay, we cancel away the time. Okay. There's any this is the acceleration of the rate of change of the velocity we cancel, and then incompressible fluid, so the density is constant. Okay. It's all back in your in your notes. Okay, incompressible rho is constant, and then steady state I have shown you just now. And then these are all the components in the x and y and the z direction. So since we are talking about only x direction only, okay, we also we deduce so many things. 2D, okay, so I just cancel. We are left with this. And if you were to clear it out a little, you just left with only this term over here, and the rest are kept constant. I didn't touch anything about it. So with this said, we can set our parameters and assumptions. One question you may ask is actually why don't you is to actually derive equation to estimate velocity of the fluid particle, because this is what we need to do, right? The question asks derive an expression for the horizontal velocity component u. So we need to derive a velocity component u, right? So you may wonder why I didn't cancel away this one. Okay, you may understand, because since I cancel away the v and the w, we say that this is y and z, right? This is also y and z direction. However, you're talking about u divided by y square now. We're not talking about any v and a u. As you can see, there's a v and w over here. Do you see any v and w over here? So apparently there is, and then this equation is actually talking about the stress in the x, y, and z direction. So it's talking about when u is moving, okay, what are the stresses acting on changing the pathway of the u itself. So it's the x, y, and the z. I may not understand much of it, but typically this is retained. But however, later we also cancel away the z direction, okay, in order to view in terms of 2D. So it's a little weird stuff over here, but just accept it first, and then we'll see how in the tutorial when you're doing it. And then so now we derive equation to estimate the velocity of the fluid particle. So you assume that it is laminar and therefore fully developed. Okay, fully developed. It's what it means is that, let's go back to this graph. It is not a very nice graph, but okay. So this is the rotating shaft. Okay, I might not draw it in a very nice manner. Yeah, this is the enlarged version of this. Okay, it's a little ugly, but okay. So this is the shaft. Okay, this is the shaft. Okay, so before it starts, okay, before it starts to turn, it is stagnant, right? When this thing is starting to turn, okay, when this thing is starting to turn, it spins, right? Just before it go to its normal speed, okay, when it start to turn, the the fluid, sorry, sorry, the fluid itself may not move that fast. So when you start to turn, the plate itself isn't, it's moving in a slightly lower u, very capital U, the velocity plate. So therefore the fluid itself may move in a slower manner. And when it starts to spin faster and faster and faster, the velocity over here is starting to get faster. And when it spins in a very constant speed or acceleration, I mean, yeah, I don't know whether velocity or acceleration, but rather than when this shaft is spinning in a constant speed, okay, it is spinning constantly with no changes, anything. So when it's spinning in a steady state, I mean steady thing, you're not, okay. So when it's spinning with a steady speed, okay, let's say at first when it's starting up, it's maybe 2 meters per second, right? I mean two radian per second, and then when it start to fully spin in the full speed, operating speed, it is always spinning at 5 radian per second. Okay, so from start up to 5 radian per second is all the transition point, and then 5 radian per second is spinning very fast. It's spinning all the way. Well, 5 radian per second is not very fast also, but I just want to convey that it is. So when it is reaching at the constant velocity of the shaft turning, okay, so when the shaft is turning at a constant speed, it is fully developed. Okay, the fluid itself is fully developed in this form. Okay, and therefore, since it's fully developed, then we can assume that constant average velocity, that is what we are saying. So this is the spinning shaft. Okay, when it is spinning in the average velocity, is so it's spinning at a velocity. And then what I mean is constant average velocity. Sorry, I didn't say properly. So um, this this is the plate. The plate is the plate describes the shaft. Hold on, back here. So this is the plate. The plate itself is just a name, but it describes the shaft. One piece of the shaft, right? One small piece of the shaft. So when the shaft is turning, the this this piece over here, u, okay, is the velocity of the whole shaft turning, right? When it is constant speed. So from this case, we can deduce that since this is fully developed, we can actually change this thing because this is some weird shapes. We're trying to make it average. So this is why we take this layer plus this layer plus this, then we divide by all these layers, and then you get an average speed. Okay, so this is what I'm talking about, constant average velocity. So I'll stop. I've said something wrong. So this is it. So just to repeat, assume laminar and fully developed, there's no turbulences. Fully developed is when you're spinning in a constant speed. Okay, it is fully developed. The fluid is moving in a constant flow of this manner. Okay, then we can assume that they are moving in a constant. This is always the speed. This is always the speed. This is always the speed. So we can take average of them and do it in this manner. And why do we want to do this manner? Okay, later I'll just explain. Our variation of velocity u in x direction is in naught. You know why? So what it means is that since it's average now, the velocity u, okay, this u or this u is the same, right? Because you're averaging this thing, the u is all the same. So there will be no variation across this thing, right? As this you can see, the u over here is different from the u over here, right? There is a variation, right? Maybe this is u0, this is ua, because u0 is at the 0 when y is equals to 0, and this is a is y equals to a, right? So this is what it means. So variation of velocity u in x direction is not in this case because there is no variation at all now because we average it. So there will be no difference in the x direction anymore. The u is constant. So this is what it means. So with this very key important set, we can actually cancel a few stuff. Okay, since there is no variation in the x direction anymore, we can cancel the force. This force is included in the x direction, right? Because it's included. But now, because we take constant average velocity, we average them out, the force is actually negligible. Okay, because there is nothing in the x direction. And then since there is nothing in the x direction also, the velocity u itself is also ignored because as I also explained that this is average, right? This is average. So therefore there's nothing changed, right? They're all the same. So there is no variation in the x direction. And therefore this is also cancelled. There is no force acting on it. And also that there is no z-axis in acting on the stress. Okay, there is a stress. Remember, this whole equation is the stress. So we actually cancel this one also, and we cancel this one since this one is x is constant. Okay, and then z is negligible. We are talking about 2D, so they cancel it away also. So this is why there's a contradiction. So since there is stress, anyway, so we just cancel z. That's all. Okay, so we are left with only the y and the pressure gradient, right? So this is the pressure gradient. I just bring this pressure gradient forward. So we are left with two terms, this term and this term. So I just bring this pressure gradient over here. Okay, so you have this set this is this. Okay, this one is this, and this is this. Not forgetting the mu over here, the dynamic viscosity. So and then I just simply bring this this dynamic viscosity downwards over here. So we have 1 over neon del partial p partial x. So this is it. We have derived a certain stage, okay, where we can start to integrate. So next video I'll just integrate this. So far you may be wondering what the hell am I doing, okay? So maybe I should do an explanation before I go on to integration. So I'll see you in the next video.